Hello, everybody, and welcome to day 2 of our Unit 7. And as it notes up here, if you haven't done so already, would you please watch the Zoom meeting from today on Schoology before taking these notes? It was a good little intro and just kind of got you a little bit background of why we will be talking about this, because our objective for today is to explain how light is produced. The connection here, of course, is just that you think of all the different versions of light that you see in a day and how many different things produce light, from anything from like the sun down to the display on the screen that you're watching right now. All of that can be explained through the chemistry that we're going to focus on today. So go ahead and at the top of your notes for today, set up your EQ. What is the explanation for how light is produced, or how do I explain how light is produced, something like that. Just a reminder, the guide for your EQ is that is what tells you how to write your summary at the end. Even though we're doing distance learning, I still recommend that you are taking paper notes in your notebook that you set up. We talked about that on our day 1 video. So just a reminder about that. So even though you're away from me, I still would recommend that you are using this as a regular notebook so that you have it for reference later. Okay, so let's get into today's specific focus. The student will be able to explain how light is produced. So the first thing we think about when we think about light is that you really can think about it in 2 different ways. You can think of it as a particle, so like a tiny little piece of energy that is moving through some sort of space, and you can also think about it as a wave. We are going to focus on light as a wave for this presentation and most of this unit. So if you're like, okay, well, how does that work? How can light be a wave? Like, how does energy produce a wave pattern the way we think of waves in science? Well, here's the explanation for that. First of all, think of what you know about electrons. Think about where electrons are. Okay, they're on the outside, and the charge of electrons is what? Negative, exactly. And then if you think about the nucleus, okay, so think about where the nucleus is. Think about what's inside the nucleus. The nucleus charge is, wait for it, yes, positive. And then you know from wherever, once upon a time, you know that when you have opposite charges, go ahead, say it. Yes, attract. Now here's a thing you maybe had not known before. Anytime you have some type of attraction, you create something called force lines. So if you see these, like here's your positive, here's your negative, and then you have these lines between them, there actually are an attraction line. You maybe have noticed this if you've ever played with one of those like magnet drawing things, like a Woolly Willy, where you put like the magnet shavings to make like the beard and the hair on the person. You might have noticed that the particles come off from that magnet wand in kind of this like curved patterns. Well, those are force lines. So anytime there's attraction, there's actually these force lines between something positive and negative. Okay, so these are all kind of like science facts that we know. Let's get that into waves then. So we know that electrons are in orbit around the nucleus, and they start at their ground state, which is like their original energy level. So if you think of like this is your nucleus and these are the energy levels where electrons can be, they start at what's known as their ground state. So these 2 electrons are in their ground state. This one electron is in its ground state. Okay, that's where they start. However, or we've talked about that electrons are moving all over the place. They're flying all over. They don't stay still. More specifically, they can go between energy levels. So if they gain or absorb or soak up a whole bunch of different energy, they're going to move up, and they're going to go to what's referred to as an excited state. So if they move up at least one energy level because they gained energy, that will be an excited state. And if they lose energy, they will move back down. And if they do that, at least one each. So if this electron were to gain energy, move to an excited state, and then at some point is like, oh, I'm too excited, I can't stay here, it will release energy and come back down. Well, if it keeps doing that over and over and over, the force lines between the negative electron and the positive nucleus, remember there was lines, those force lines between them. So as this negative electron moves, so kind of imagine this with me, get your imagination working here. So imagine that you had this negative electron that is now moving up and down, up and down, up and down. That's also, just a second. So when that negative electron moves up and down, up and down, up and down, those force lines are going to move also. And when that happens, that's when you start to see a wave. So because those electrons are attracted to the positive nucleus and there's force lines between them, as those electrons move up and down, those moving force lines also produce a wave. Okay, so then the next piece is, okay, so this is a general wave pattern. Why do we get different patterns? Like, how can we get some that are really, really close like this and some that are more spread out, different patterns, different sizes of waves, all those kinds of things? Well, here's a few different reasons for that. One, you can have an electron that moves up or down more or less energy levels. So you could have an electron that goes from 1 to 2, or from 1 to 3, or from 1 to 7, and then from 7 back to 6, or 7 back to 4, or 7 back to 2, or 4 back to 2, etc. Right? That's the idea. So because there's many different energy levels, and depending on how much energy an electron absorbs, how far it moves up, how far it moves down, that can give you different patterns. Another thing would just be how fast the electrons are moving. So if you think back to the demos that I did at the beginning in our Zoom meeting, those glow-in-the-dark things, they are moving slower, so then it's a different version of a wave pattern that they're giving off. And then the other big piece of it is just how many electrons are moving. So if you have something like hydrogen, hydrogen has one electron. That one electron can move to different levels, but it's always only ever going to be one electron that is moving and producing energy. But if you had something like potassium, which has 19 electrons, you have so many more combinations of electrons that can be moving up and down, how far they're moving, and so you just produce a much different amount of energy. So those are all the different reasons. So the reasons you get different kinds of patterns or different kinds of waves would be because, well, how far are the electrons moving, how fast are the electrons moving, and how many electrons are moving. So that idea of, okay, how is light produced can kind of be summed up in those 3 steps. You have an electron, it starts in its ground state. It gains energy and moves up at least one energy level. That's its excited state. It can't stay there, so it goes back down. When it goes back down, it wiggles the force lines and creates a wave pattern. And that's what we would perceive as light. So that's kind of the summary that you're going to think about today is, well, how do we produce light? That's kind of the idea. Okay, so why don't you go ahead and take a little break, go ahead and pause the video or come back to this later and do a level 1 kind of question. So something straightforward, right from the notes, a definition, listing, why do we get wave patterns? That could be a level 1 question because it's right in your notes, but something level 1. Go ahead, pause and do that. All right, welcome back. The next thing I want to talk about is just like the general structure of a wave in case you need a review, because we'll refer to some of these terms later. So your first thing I want you to be aware of is what we refer to as wavelength. The symbol for it is the Greek letter lambda. It's kind of like an H or an upside down Y, however you want to think of it, but usually we draw it like this. You kind of drew a hook with just a little tag there. So wavelength is when does the wave start repeating? So this, like how long the wave is, we don't think of that as wavelength. We think of that as how high and low is more like amplitude, right? And that's really like amplitude is like how high it is up from kind of like the axis, if you think of it that way. Wavelength, though, is when the wave starts to repeat. So here the energy is going down, and then the energy is going back up. That's the wavelength. So from one, here's another term, one crest to the next crest, or one trough to the next trough, those would be wavelength. So those are just some terms that you might be familiar with already, but I just want to make sure we're all in agreement. So this is a general wave pattern, and those are terms we'll use when we describe different wave patterns. Related to different wave patterns that you might be familiar with is something called the electromagnetic spectrum or electromagnetic radiation. So just to clarify, light, any type of light, not just the light we can see, because as kind of regular citizens, people think of like, oh, the light you can see, but that's only one piece of the electromagnetic spectrum. Perhaps you have seen something like this. So like radio waves, microwaves, infrared, visible, all the way up to gamma or cosmic rays. Those are all referred to as electromagnetic radiation, and they're all referred to as light. So the science definition of light is any of these types of wave pattern, not just the visible patterns that we can see. So just to clarify that. Okay, now let's go just a little bit more in depth. Radio waves would be a type of energy that generally we would say is pretty much okay for our bodies, which is good because think about all the different radio stations and different things that are giving off radio signals that are around our bodies all of the time. Generally, that energy is not going to be enough to change any of our cells and cause any problems. And then as you go through the different parts of the spectrum, microwaves a little bit higher energy, infrared a little bit higher, and then you get to the wavelengths that our body can actually see, our eyes can detect. And then just a reminder that they go in order for colors, red being the lowest energy, and then violet being the highest energy color that our eyes can detect. And obviously there's differences in there in terms of how well you can see them. That's different, different body types can sometimes notice different things better. But that Roy G. Biv acronym is a really nice way to remember the order of energy colors. And if you're having a hard time remembering which one, is it red or violet that's high or low energy, remember that the next one is ultraviolet. And ultraviolet is something we know as UV rays, right? And generally that's not so good for our body. This is where sunburn comes from. And so that can help you remember that, well, okay, yeah, ultraviolet UV is the stuff that burns our skin from the sun. And that reminds us that, oh, violet must be pretty high energy then. So violet is the highest energy our eyes can see. Red is the lowest energy that our eyes can see. And then it just keeps going. X-rays, maybe you've noticed or remember if you've gone to the dentist and you've had to get X-rays for your teeth, they put that lead apron on your body first just to kind of to protect some of your internal organs, because getting a whole bunch of X-rays blasted at your body all the time, that amount of energy could cause some problems to your cells if it was happening a lot. And then if you ramp that up, let's use a great example from pop culture, gamma rays, even higher energy. This is what happened to Bruce Banner to turn him into the Hulk. So even though this is a story, there is actually some science there. So if your body was blasted with a bunch of gamma rays, it absolutely would be able to change your cells, which is of course what, is the storyline for Bruce Banner. And then cosmic rays, of course, that would also be super bad for our bodies. We don't really need to worry about that because as the term cosmic implies, it is out in space. So just to kind of give you an idea here, so radio waves would be our lowest energy types of waves. Cosmic would be the highest waves, with all of those in between. So then to kind of give you a visual related to that, so radio waves being your lowest energy are going to have a low frequency, that's the symbol for that, and a high wavelength. So let me show you what I mean by that. And I apologize, I know we haven't talked about frequency yet, but we will talk about that now and later this unit too. So if you imagine drawing a wave with your finger, like in the air, like kind of what I'm doing with my mouse right now, notice that it doesn't take me much energy to do this. It's a long spread out wavelength and it's not repeating very quickly. So low frequency. This is how we know it's low energy. And then it just ramps up from there. Microwaves are a little bit higher, infrared a little bit higher, visible, UV, X-ray, gamma, up to cosmic rays, which would have a high frequency, meaning they repeat themselves very quickly, and a low wavelength, meaning they're really close together. So again, if I want to draw this, notice that I have to use a lot more energy in my finger to trace with the mouse. So if you were drawing that in the air with your finger, you would notice in your body, you would need more energy to draw a cosmic wave than a radio wave. So long wavelength, low frequency, low energy, short wavelength, high frequency, high energy. Just to kind of give you a connection between wavelength, frequency, energy, and these different patterns of waves as we try to describe and understand light a little bit better. All right, go ahead and either pause for now or come back to it later. A level 2 kind of question. Explain, compare and contrast, draw or sketch would be a great example. Draw a microwave compared to an X-ray. That would be a great example of a level 2 kind of question. All right, go ahead. Welcome back. Okay, the last piece of our notes for today are we're going to explain the demos that I did during our Zoom meeting this morning. So I'm going to call them great light tricks. The first one we're going to do is fluorescing. So if you remember from the Zoom meeting, this would be like black light stuff. So any type of that light glowing that you see under a black light. Well, here's what's happening. The electrons in whatever chemical that you're dealing with, so whatever electrons are in the shirt or the detergent or the chalk or whatever, they're absorbing UV energy. But when the electrons go back to their ground state, they're giving off energy in the visible region. But there's more energy than normal in the visible region, so it seems to glow. So because it got extra energy from the UV light, the black light, then when it drops back down, back to the ground state, it's releasing energy, but that energy is a little bit lower level than UV. It's in the visible region. And then that makes it seem brighter than normal. So that's fluorescing. That's black light stuff that you've seen. The next demo I did was phosphorescing. This is your glow-in-the-dark stuff, right? So the idea here is that the electrons are getting energy from a light source, and then they're gaining energy and moving up to their excited state. But they don't want to stay there because at some point the energy goes away, so you turn off the light, and then it glows in the dark because the electrons take a while to go back to their ground state. So if you kind of follow my mouse here, so imagine this is my ground state. This is where the electrons inside the object are located. They absorb energy, absorb energy, absorb energy, absorb energy, and they go up to an excited state. And then at some point you turn off the light source, and then those electrons slowly go back to their ground state. And then eventually it'll stop glowing when all of the electrons are back to their ground state. For fluorescing, the electrons stop glowing when the UV source is gone, because it doesn't have enough energy in that visible region anymore, so it doesn't glow. And then the last demo I did was chemical luminescence. So this is your glow stick kinds of things, right? So the electrons are absorbing energy from a chemical reaction, and it has to be exothermic because that means energy is being released. So then the electrons are taking that released energy and allowing them to get up to their excited state. At some point, they can't stay in that excited state, so they release the energy. It releases in the visible region, and it goes back to the ground state. So then it glows as long as that chemical reaction is happening. When the chemical reaction is done, then you're not going to see that glowing anymore. So depending on what chemicals you put in the glow stick, that will determine how long the reaction lasts and also what colors you see. So all of them go in this general idea, but it depends on what chemicals you're using in terms of how long it lasts, and then also what colors you'll see. So going back to, maybe you've heard this trick like, oh, if you put the glow stick in your freezer, it'll last longer. Well, technically that is true, because if you think about what we know about kinetic theory, in the freezer, the particles are going to move slower. That means the reaction is going to go slower, which means it's going to take longer time for it to finish the reaction. The trouble is, obviously, it's in the freezer, so nobody can see it, so it's not that interesting anyway. Okay, and then related to chemical luminescence that I wanted to just make sure that you're aware of is something called bioluminescence, which is really chemical luminescence in a living thing. So maybe you've seen Finding Nemo, like that deep sea creature that has the lure that they can't see the body, but the fish or whatever can see this bioluminescent lure, and then the fish come and are attracted to that, and then the deep sea creature can eat those fish. But also a firefly. So in the firefly's bottom, it releases chemicals when it is nervous or startled, and then that chemical reaction is a bioluminescent reaction that glows. So little fireflies, when you see them giving off light, it could be because they're trying to attract a mate or a family member, but that's also, again, because they're like nervous or excited. It also happens if they are like startled upon, like if you go walk by a tree or a bush that has fireflies on them and it's nervous and it's scared, it will start to glow, which it's not a great defense mechanism because now you know where they are, but we generally leave them alone and they're safe. So those are some fun things related to light, all going back to the idea of anytime you see light, there has to be gained energy, electrons have to move to an excited state, and then they have to come back down. So that's kind of the general way light is produced, any type of light source that you see. All right, go ahead and do a level 3 question. So some type of judgment or imagine if or those kinds of things, those level 3 questions. And then after that, your summary today should be an explanation of how light is produced. And generally see if you could do it in that 3 steps. All right, that ends our video notes for today. So that's the end of day 2. Feel free to go back and watch parts of the video if you need to, or maybe you just watched it the first time and the second time you're going to go back and now take notes. That's up to you. But your to-do list for so far would just be, we'll finish anything from day 1, which is really just that Miss K remember me assignment, but also setting up notability, like any of that stuff. And then you could do your classic questions and summary from your day 2 video notes from today. There's no other new assignment for now. So those are things you can take care of. And then I will see you at our next Zoom meeting. For those of you that in hour and 1 and hour 3, that will be Friday. And then those of you in hour 2 and 4, that Zoom meeting will be Monday. So have a great day. Welcome to the end of day 2. We will talk to you later.